Okay, so, the last time, we talked about, some of the homomorphism theorems that you all, see for, that you all have seen this for groups. And now we're going to see it for modules. So let's start off with the big. Let's suppose that F A to B, the R module homomorphism. Okay. Then F induces an R module homomorphism. R module isomorphism, that is. F bar from A mod kernel of F into the image of F. Given by okay, my input is a coset out of here. I need to get an output in the image of F. What's the easiest thing for me to do? That's right. Never do anything if it's not easy. And there we go. This is probably a familiar theorem just in the context of groups, right? Y'all know this one from the group theory days, right? From previous 8510 or whatever algorithm I have, we know that F bar from A mod kernel of F into the image of F is an isomorphism of the groups. Actually, this is really easy to show because of the fact that F is assumed to be already a homomorphism. What does anybody remember? What is the key thing to show in the proof of this back when you did your groups? Right, that was the big thing. Is the fact that F bar that was really it, is just show it, because remember, the input here is coset, right? So you have to show that if you have two different choices of coset, then you get the same output, right? And showing the homomorphism part is not very difficult. But stop me if you want me to do some of this. The last little piece of the puzzle is this honest to goodness, an all-American, old-fashioned R module homomorphism? So well, so let's look at F bar of R. Well, this is F bar of RA as kernel of F, this coset, which is F of RA by definition, which is R F of A, since F is an R module homomorphism, which is R times F bar. So there you go. This is an R module homomorphism. Okay. So as a fun challenge to you all, use the first isomorphism theorem to show parts C and D of the previous theorem. Let me give you one corollary to this. to all this business. If R is a ring, unitary, of course, and B and A are R modules. Then there exists a one-to-one correspondence between submodules of A mod B and submodules and let me R submodules of A mod B and R submodules of A containing and the correspondence is given thusly. R submodules let's say C, where so see if you can see if you can verify this. I hope, now correct me if I'm wrong, but I hope that this all is familiar because you've probably seen all of this in terms of groups or billion groups or whatever. Okay. Okay, any questions? Okay. So probably modules more than anything else, these kind of universal constructions are important. So direct products, direct sums, I'm gonna define these and distinguish between them. We're gonna look at some other universal constructions. How many of you have seen the construction of the tensor product? Oh, good. So you guys, I don't ever say I never gave you something. So we'll get to that in a bit. So again, I am going to stair step up a little bit, but let me know if this is a little bit shaky in your past. There. Start off by thinking of direct product and direct sum in terms of a billion groups. And yes, always a billion groups. Let AI be a family of R modules. So in other words, just some big fat collection. We'll just think of this as a billion groups at the beginning. And direct product and direct sum, respectively, of the family. AI as a billion groups. Let me take a little aside here just to make sure we're all on the same. Can anybody tell me what's the distinction between direct product and direct sum for Billion groups?
Some only a finite amount of terms are non-zero.
Right, so let me write a typical element. So each AI. So this is like a generalized sequence because this index set or a net, this index set might be uncountable, might be very, very large. You can go hog wild here. Yeah, any AI in AI, you can put anything in here you want. To be in direct sum, AI is equal to 0 for all but finite many. So this sequence, this generalized sequence, has to be mostly 0 entries, all except for a finite number. Notice that if this index set is finite, there's no distinction here, right? This sounds like crazy crap, right? It sounds like somebody made this up. Why should we fill this mostly up with zeros, right? This is just something that some evil algebraist made up so Jim can ask more homework problems or some kind of stuff like that. But it turns out that this is very important, as a matter of fact. In fact, in certain sense, direct sum is, well, I mean, it depends on who you talk to, but I think direct sum is sort of more important because it turns out that any R module is a homomorphic image of a direct sum of some number of copies of R, which is kind of cool, right? So in a certain sense, the direct sum is sort of the father of them all, so to speak. So let me continue. Now that I hope we're on the same page with what these elements look like. This direct product is an R module with R action given by R the direct sum of AI is an R module. Well, let me rephrase. So just the direct sum is just that particular submodule. Notice that if here almost all of the AIs are 0, and that's certainly true when you multiply this here. And let me also say that when we talk about direct product and direct sum, and I fall into this trap too, I think of it usually just as these constructions here, right? Just these things. But technically, the direct product and the direct sum aren't just these objects. They come equipped with certain homomorphisms, as I'll explain here. C. For all K in our index set, the canonical projection let's say pi K from the direct product of AI into AK canonical projection. This is just the map that reads whatever the K coordinate is, if you will. That is to say, pi K it takes this huge thing and reads it, and it just barks out whatever the K entry happens to be, right? This is an R module epimorphism. I guess this probably has to put a little bit more thought into this one. I won't prove this. This is pretty easy to show. We already know that these are abelian groups, and this R actually makes an R module. Here, it's pretty clear since what this does is this focuses only on one of the coordinates, the K coordinate in particular. This is it clear to you all that this is an R module epimorphism? Right, it's certainly on to, because given any AK and AK, just the sequence of all zeros and then the AK and K coordinate maps to it, for example. And B for each K index set, the canonical injection iota K, that's supposed to be an iota, Greek letter there, from the direct sum, or from A K into the direct sum, given by, well, let's see here, this one I gotta think about a little bit more. Iota K of AK, well, my output has to be something in the direct sum. So I'm gonna call this XI. And how do you suppose I find XI? What's the easiest thing to do? All zeros except where I need this to be a K, right? Zero is an R module monomorphism. Okay, so there's kind of my introduction. So actually, technically speaking, the direct product of a family of R modules, AI, is this object, this big object here, and all of these projections, right? So for each K in the index set, you have this canonical projection here. So the direct product is technically the object that is the direct product equipped with all these homomorphisms, and the direct sum is the object coupled with all those one-to-one, those injections. Okay. So let me give you a theorem. I've got two dual theorems, one for the direct product, one for the direct sum. I'm going to prove the direct product theorem, and I'm going to leave as an exercise the direct sum because it's very similar and it might be good practice to do. So let me get all the bells and whistles here. Theorem. This is sometimes called the universal property of the direct sum. Let R be the ring and say AI I'll just change my index set to that. a family of R modules. Let's see an R module. And let's say that we have a family of homomorphisms. From C into AI. Okay, so here's the situation. You have this big collection of R modules, say AI, and you've got some other R module C, and some fixed R module, and you have this family of homomorphisms from C into AI, right? Now, this bothered me the first time that I ever saw this when I was an undergraduate. And the first thing that leapt into my mind is, boy, this seems kind of restrictive, because how do I know that I have homomorphisms from C into AI? Somebody tell me why this is a rather silly thing that could be put to rest really quickly. Well, if nothing else, you've got the zero homomorphism from C into AI, right? So existence is not a problem here, right? So given the C, I certainly can't find an infinite family, because if nothing else, you can take some of those PIs to be zero for all of them, right? Okay, then there is a unique, there exists a unique R module homomorphism let's call this B from such that that diagram is such that when you do phi, then pi I is the same thing as doing each phi I for all I and I. Product is uniquely determined up to isomorphism. Okay, so this is sort of the universal property of the direct product. The direct product has this property, and this last statement means that the direct product is the only module you can build up to isomorphism that actually has this property. Let me draw you a picture. I do like pictures. So here's the situation. So what do we have? We have these phi i's that go into, actually, let me display. Let me distinguish. So we have all these phi i's. I'll pick one phi k. Right? We have this. And notice that we have a projection map from the direct product on the K. This is what did I call it? Top K. Right? What this theorem says is, given this family of homomorphisms that we had here, and these projection maps here, then there exists a unique phi such that that symbol means the diagram is. That is, when you do this and this, when you do phi pi k, it's the same thing as doing p k, and this works for every k index. This is kind of my nice picture of this, if you will. This sounds really fancy, doesn't it, right? Oh, look, these big universal statements, given any family of R module homomorphisms, then there's one and only one homomorphism from here into here that makes a diagram compute. And this construction's unique with this property. Well, I'm gonna bravely step out here and just tell you how this is gonna work. Let's see if we can figure out. I'm gonna build this homomorphism, and essentially, here's the way the proof's gonna work. This is the only way I can build this homomorphism, right? So let's see what has to happen. Well, suppose you start with some C here, right? Well, this goes over here, somewhere. But I want the diagram to commute, right? And so what happens when I go over here? I don't know much, but it has to be some sequence or some generalized sequence. And then it has to project here. Right? So what does this mean about xk? Okay, there's a whole bunch of coordinates here, but let's go one step at a time. Let's just look at the kth one, because here. What does this mean about the kth coordinate here?
It's equal to PKC.
It has to be equal to whatever the image under this fixed homomorphism was, right? There's no choice there, because what this map does is this actually reads the kth coordinate, so it has to be that, right? Now, this little pretty picture works for every k in the index set, right? So what does this have to be? We've got no choice really to be, this has to be of C. That is my homomorphism of choice there. Let me just do a couple of details here. Well, if you look at this right here, this is the sequence PI, P1 plus C2. But of course, each one of these PIs is itself an R module homomorphism. And by definition, I can break this up because this is an element of the direct product. So this is and to show that this is actually, so that shows it's a homomorphism with respect to the abelian groups. For the other one, but of course, again, each one of these is our R module homomorphism. So this is R phi C. And you can suck that R out. Now I've got this sort of common factor, if you will. So this is an R module homomorphism. Probably no shock there. Now, I did say, unique, right? So let's do that. Now suppose that whatever that group letter is, another homomorphism, C to AI, that makes the diagram commute. That is to say that, suppose we have another such, solution. Well, notice that this is very similar to what I wrote in orange over here. If you look at I don't know much, but any other homomorphism like this, again, its output has got to be some collection of elements over here in AI. And notice that pi I is equal to CI. Hence, each CI so basically, this is what we kind of guessed before. The conditions on this forced us into there's only one of these things. Now, here is the last statement. So now I want to show that this direct product construction is unique up to isomorphism. And I think that this is a really kind of cool figure. So I'll leave my picture up here. So let's suppose that we have another solution to this universal mapping problem. Suppose it is another solution to right. So the direct product of this family is a solution in the sense that if you put this in here, you've got this unique homomorphism that makes the diagram commute. Suppose that we've got another construction, maybe possibly different than the direct product, that has this property. So we have the diagram. So. Okay, the index set, right, we have this diagram, right, where this is. And this is the projection map here, right? Now, this has to work for any module and any collection of homomorphisms, right? Given, no matter what C is, then this is a solution to the problem, so you can complete the diagram, and so is D, right? So in particular, let's do this. Let's replace C and collection PI and C and AI, replace C by D. So we have C solution here. Notice these are the projections. So here I've chosen Z and instead of C, I've chosen the specific D and where the projections are, right? Can anybody tell me a solution to this? Okay. And because this satisfies the mapping property of the direct product, then that solution should be the only solution, right? That it works and it's unique, so there you go, right? So now let's augment the diagram in the following sense. Let's consider this. Now, I'm gonna draw this diagram here, and maybe try to tell you where it came from. We have projection maps into AI, or and these are the projection maps from D here. So basically what we have is, now C is being played, here by this, and then D is being played here, right? Because, so basically what I think about it this way, this is here, the role of C is being played by D, right? And this map goes into the direct product, right? Call it F. And here, what we have is, now we've got this being the role. Let's see which one already. Right, so this is also, so we've got this right here because this is C and we've got the direct product of this, but D is also a solution to this. So we have, now we have C being played by this, and we have this map here. Everybody understand what we did here? Basically, playing off of both of these, since both this and this are solutions to the mapping problem, Now, everybody okay with this so far? Now, I'll do this composition here, which is do F first then G, and ignore this middle bit, and what we have is the same triangle right here. Everybody ready? And so what does this mean? Well, this has to be the identity on D, because that's the only solution. So what do we have here from this? Everybody okay with that so far? Now, what's good for the goose is good for the gander, right? Here, I played this triangle out this way by letting D play the role of C and then this play the role of C. But I could do it the other order too. Right? So I also have again, by the same argument we had before, this has to be the identity on the direct product of AI. So what we have now is we do G and F. So what do we have? GF, or yeah, GF is this bijection. FG is this bijection. Therefore, F is, well, actually, it's us. G. And so any construction that you do, this has to be explanation correct product, right? I mean, don't you feel like you need a shower, right? It's like I feel a little dirty, like I got away with something here, right? But this is really one of the cool things about this. Okay, any questions on that? Let me give you, and I want you all to pay attention to this. This is often, this is kind of a dual notion. And in the late 50s, probably through the 70s, a lot of people made a good mathematical living on doing this kind of thing. Let's reverse some arrows here. Theorem. And I'll let you all prove this yourself. It's a fun exercise. 6, 1, 3. Let's let R be a ring and AI a family of R modules again. R modules. Let's fix an R module. We'll call it D. D and R module. And I've got its collection again. R module homomorphisms. Then there's a unique there exists a unique R module homomorphism say pitchfork from the direct sum AI into D. Such that pitchfork iota sub k is p sub k. And then so, and as before, the direct sum AI is uniquely determined. Up to isomorphism by this property. So notice that this is basically the previous theorem with the arrows pointing in the other direction. That's essentially it. Let me draw you my patented picture of this. So what do we have here? We have this family of homomorphisms here. We have these canonical injections, iota sub k, we go into the direct sum. And what this gives is this homomorphism that we call. Goes here, so it's the diagram. Mutes, that is to say, pitchfork, doing iota k pitchfork. Okay. Any questions on that? Okay. So try to prove this one. It's very similar to the previous one in pretty much all aspects. But of course, the iotas are a little bit different. You have to think about this. Let me give you a last theorem for today that I think is a rather practical theorem because these are like super cool, groovy theoretical theorems that have application things. But here is the working person's get your hands dirty way of telling things about a direct sum. So this is kind of the practical computational skill. Proposition 634. Let R be a ring. And AI, a family of R modules. And I suspect that you've seen something very similar to this in the context of just affiliated groups, and so this won't be a great deal different. Well, let me see. Say that right. I want to say R submodules. They so you've got this family of submodules, all of there are submodules, some parent module A, such that A is the sum of family AI. That is to say, A equals sum. And remember what we mean by the sum. This is a finite sum where that is a finite sum of things in AI. And number two, or number B, for all K in the index set, A sub K intersect A K bar is 0, where AK and bar equal the sum of AI so AK bar is the sum of all modules that are not AK. Then if that family satisfies these two conditions, then A Yeah, it's isomorphic to the roots. And we'll talk about this next. Any questions? Any questions? Everything reasonably clear so far? All right, well, give me a holler if you get hung up, and we will see you by Friday.